Mic test. 1, 2. All right. I can hear myself. Well, we're gonna have bit devs today, and it was canceled, but my stream is not. So I'm essentially just making a YouTube video. Here, let's switch scenes. All right. Hello. Welcome. Okay. Don't want to confuse anyone. Let's go slideshow. All right, now this is a pure Twitch stream. So what that means is no in-person viewers today. Again, because BitDevs was canceled, but I came here early. I was happy to beat the trucks and come extra early. But let's just get started. So this is Understanding Bitcoin Source 15. I'm doing it this week because I don't want to do it next week, and I committed to today. So the topic is the interpreter in script. I was gonna have an interesting idea where I use ChatGPT to ask questions that a random person might have, but I don't quite know how I want to implement that. Yeah, I don't know. But essentially, I'm making a YouTube video. That's what this is. And if there's someone who comes live, feel free to comment. So the interpreter in script. So what is Bitcoin script? So I don't know who knows about Bitcoin script and who doesn't, but I decided to give a little explainer here. Satoshi said a script is a stack machine, like Forth, that evaluates a predicate returning a bool indicating valid or not, and there are no loops. So some of you may know this, but there are no loops in Bitcoin script, which is what prevents it from turning into something like Ethereum. And it's based off this thing called Forth. Now, this is kind of a wordy statement, so me personally thought it would be a good idea to try and break it down to make it more accessible to anyone who's reading this. So, first part, let's start breaking it down. Script is a stack machine, like Forth, that evaluates a predicate, returning a bool indicating valid or not. Anyway, the first part of script is a stack machine, like Forth. So let's focus on that. Programming languages are grouped together based on what they do and how they accomplish things. So for example, languages like C++ and HTML are very different from one another, since C++ is something called an imperative language and HTML is a markup language. And just like C++ is classified as an imperative language and HTML as a markup language, Bitcoin script is classified as a stack-oriented programming language. Okay? Maybe that still causes your head to spin, but just know that script is a stack machine like Forth is just stating the type of language that script is. Now, the next part, that evaluates a predicate returning a bool indicating valid or not. Okay, well, what does that mean? From Wikipedia, according to Gottlob Frege, however you say this guy's name, the meaning of a predicate is exactly a function from the domain of objects to the truth values true and false. Now, I don't know if that helped you get a better understanding or not, so I actually put my own explanation. Mine is that a predicate is some expression that outputs a true or false. An example of this would be the expression, is 8 greater than 6? Is this true or false? Feel free to answer at home when you're watching the video, but this answer is true. The returning a bool indicating valid or not follows the meaning of a predicate, and it's actually somewhat redundant, but I'll give Satoshi a pass. All right, now this final part, there are no loops. This is very, very important for the language, for the system to work. Otherwise, again, we'd have an Ethereum. And why is Ethereum bad? Whether it's bad or good, I guess it's subjective, but I think it makes it subjectively worse. So This is one of the most important decisions made about Bitcoin's design, and is what separates it from other cryptocurrencies like Ethereum. This was intentional from the beginning, and it prevents Bitcoin script from being a Turing complete programming language. If you don't know what that means, all you need to know is the problem with Turing complete programming languages is that it is impossible to know whether they'll terminate or not. See the halting problem if you've ever heard of that before. But in Ethereum solves this issue by treating fees like gas and saying they'll only execute as much computation as you pay for. And as if you've ever looked at the Ethereum blockchain, you see that there's complexity when trying to estimate how much gas you should pay for a transaction. And this complexity doesn't exist in Bitcoin because it is not Turing complete, no loops. So why was this added to Bitcoin? This being Bitcoin script. Why was it added at all? So the motivation for script. This is from Satoshi's mouth himself. The nature of Bitcoin is such that once version 0.1 was released, the core design was set in stone for the rest of its lifetime. Because of that, I wanted to design it to support every possible transaction type I could think of. The problem was, each thing required special support code and data fields, whether it was used or not, and only covered one special case at a time. It would have been an explosion of special cases. The solution was script, which generalizes the problem so transacting parties can ascribe their transaction as a predicate that the node network evaluates. So pretty much Satoshi wanted to add all these things to Bitcoin, but he didn't feel a need to limit himself in making specific use cases. He said, why not just make a programming language such that anyone could go and build out their own use cases, because this thing is robust enough to make an expanse variety of spending conditions. How is Bitcoin script used in Bitcoin? So I gave a brief introduction to Bitcoin script. Now it would be good to know how it's used in Bitcoin. So every transaction in Bitcoin is associated with a script placed in a section called the script pub key. I love this word. I think it's great. A lot of people are unfamiliar with it, and it's funny because you can see who's ever looked at the technical details of a Bitcoin transaction by asking them, if they know what a script pub key is. So scripts determine who's allowed to spend a transaction. That's what this field does. When sending Bitcoin, the recipient of a transaction defines the script, or really the wallet the recipient uses, because no one's manually putting things in. And no one can force covenant locked coins on you because, again, the recipient chooses which script to lock the sender's coin in. And addresses are made from these scripts, and these scripts are sometimes implicit with their behavior. So the mechanics of spending a transaction. I'm gonna go and talk about the script pub key again here. So the script pub key. This script is what prevents the unauthorized spending of Bitcoin transaction outputs. Most of the script pub keys you will use are just check sig verify calls to check that you have a valid signature over the transaction. So people say your keys are the most important thing in Bitcoin. It allows you to spend transactions that were sent to you, and without them, you have nothing. Not your keys, not your coins. It's a promise, especially if we're looking at custodial solutions. So not your keys, not your coins comes from this usage of script to try and verify your transactions, because there's a locking script, is what I like to call it, that says this thing can only be spent if a signature is provided for the public key the sender was sending to. So here's an example of an implicit script. So this is from bit 141, which is a specification for SegWit, or specifically SegWit v0, because SegWit v1 is something called taproot. So here's from bit 141. This stands for pay to witness public key hash. The following example is a version 0 pay to witness public key hash. So this is kind of what I meant by implicit scripts. Since I spoke about check sig verify, I wanted to go in detail about like a script that could be implicit. So the witness is going to be a signature and your public key, and your script sig is going to be empty, and your script pub key is 0 and a 20-byte hash. So let's break this down. When I would like to use an implicit script, what I can do is I could get a 20-byte key hash of my public key, and I could set it into my script pub key. It actually follows a 0. So first I put a 0 to indicate that it's version 0 of the witness program, and then I put the 20-byte key hash. And the length of the witness program right here indicates that it is a pay-to-witness public key hash type. So they kind of call this hash the witness program, but again, it's just the hash of the public key that my wallet owns. So I'll use this script pub key to make an address and give it to some sender who wants to send me money. And now I have, once he makes that transaction, I have an output that's locked with this script pub key. Then when I want to spend from that script pub key, I will provide the public key that my wallet was managing for me that was used to make this hash, and I also provide the signature. Both of these are done by my wallet. As a user, I don't need to know what's going on, right? And yeah, it's verified as if I just did check sig, pub key, and signature. Even though the script pub key here doesn't contain the scripts, it only contains a 0 and the 20-byte key hash, it implicitly represents this expression so that when I'm actually spending it, it will put in check sig semantics and use the public key and signature that I specified in the witness. But maybe I'm jumping the gun because all this is SegWit involved. And I have a special section for SegWit in this presentation. So just to emphasize that script pub key exists on a transaction output, I got a transaction from mempool.space, and you can see the inputs and the outputs. And there is a script pub key on this output. So it's pretty cool. And here are some operations that you might specify in your script, like opdup, which stands for duplicate, or ophash 160, which just hashes, this is a push bytes 20, and so on and so forth. So now the script sig and the witness are what I want to go over next. So the script pub key, going back, so this prevents the unauthorized spending of Bitcoin transaction outputs. So the script pub key is a script that exists on the output of your transaction. Now the script sig kind of contains data that should satisfy the script pub key on your output. So let's just read what's here. When spending a transaction, data must be provided in a section called the script sig that contains information that satisfies the previous script pub key, so of the output that you're spending. This part used to allow any command in script called opcodes to be placed in it, but this soon changed with BIP62 to only allow data to be pushed, unless pay-to-script hash is used. So for SegWit transactions, this is a little bit different, but the data needed to satisfy the script pub key, so any unlocking data needed to satisfy the script that you specify in your output was moved to the witness, and the script sig must be empty. And I'll go more into that a little bit later. But all you need to know is when you spend Bitcoin, you lock it in an output that contains a script pub key. The script pub key is an expression, a code expression that will get run when you try and spend the output. And to satisfy that code expression, you typically need to provide information either in the script sig for legacy transactions or in the witness for SegWit transactions. Now, how does Bitcoin script work? So a script is typically a sequence of operations like so. You have push data 1, size, data 1, and then push data, that should be, push data 1, still okay. Push data 2 size and push data, or data 2, and then a command. Maybe not the easiest syntax to work with or present with in hindsight, but this is what I put there. It's just an example of how a program might look. Pretty much pushes data and it operates on the data with these commands. Now we run scripts of this form from left to right. When a data push operation is found, imagine us stacking the data in a section called the stack. So data 1 would get stacked first, and data 2 would get stacked on top of data 1. So I run this command, push data 1. How big is the data I need to push? Okay, it's in data 1 size. I read that, and I push data 1 onto the stack. Then I read another push data 1 command. I want to read in the size of the data I should push, and then I push data 2 onto the stack. Now this command should operate on these two stack elements. When a command is found, it will usually operate on the data found in the stack, what I just said, and the operations are referred to as opcodes in the code and stand for operation codes. Nice to know what it means. So I differentiate opcodes between being something called a data push opcode and a command opcode. And I would like to go into why I make this difference and what the difference is at all. So let's go over data push opcodes to start off to see what that means. So push data opcodes. There are 3 official push data opcodes. There's push data 1, represented by byte 76, push data 2, represented by byte 77, and push data 4, represented by byte 78. So these are the official push data opcodes. Again, these are kind of different from what I classify as data push opcodes, although push data opcodes are included in my definition of data push opcodes. The number after the push data represents how many bytes need to be taken to read in the size of the data. So it's not the data itself. When you have 1, 2, and 4, these numbers represent how many bytes represent the size of the data that we need to read. So push data 1 can read a max size of 255 bytes. Push data 2 can read a max size value of 65,000 bytes. And push data 4 can read a max value size of 4,294 blah blah bytes. And obviously, you actually can't fit this many bytes in a Bitcoin transaction. So I'll elaborate on that further in the next slides. So this number is then used to determine the number of bytes that need to be read from the script and put onto the stack. So everything else I call push data isn't really called that in the code. If I refer to a data push opcode by accident as push data, then just know it's not an official push data opcode. These are the official push data opcodes. And again, these sizes are crazy because Bitcoin transactions cannot be this size. That's just not, consensus valid. And here we go. You will never need push data 4, or really anything past 1. So here is a Bitcoin Stack Exchange post by Christian Decker, C. Decker, on April 12th, 2016, talking about op push data 4. There is currently no real need for an op push data 4, which would allow pushing up to 4 gigabytes onto the stack. It was in the original script definition and simply was not disabled when the 520 byte limit was introduced. The only possibility for it to appear in today's scripts is as non-minimal push and may be caused by custom client or transaction malleability. Pretty much these other push data opcodes don't need to be used. You have a 520 byte limit on what can be added, right, to the stack. So yeah, these don't really make any sense. You don't need them. All you really need at most is push data 2, I guess, for the values above 255 to 500, but you definitely don't need its whole range of values. Not only do you not need it, it's impossible to use the max value here. So implicit data pushes. Any byte value below the value of push data 1, which represents the number 76, will be implicitly read as a size, and the next 0 to 75 bytes will be read from the stack. So push data 1 is its opcode by itself. Whenever you see a push data, it means there's a size coming next. After you read the size of the data, then you actually read the data that is part of the script or script sig onto the stack. So push data comes first. You in your script, it looks at the size right next to it, and then it reads in however much data that the size represented. But instead of using push data 1, you could actually just put a value below 76 to represent the size. So you could actually just omit the push data if your size is small enough. So here's an example. You start with an expression in Bitcoin script. Like, let's just say we have the value 2, and then we have 0, 1, 0, 0. This should be the value 255 in hex. Hex is a format of data that essentially has two of the characters representing 1 byte. So here is the 2. If this was my Bitcoin script, I'd look at the 2. I'd say, okay, since this is a number between 0 And 75, this is a size for data that the script wants me to read onto the stack. So I read the 2, and then I pretty much read 2 bytes off the stack. And since the only other things on the stack are 0, 1, and 0, 0, when I read those, you know, they're all put onto the stack. So read opcodes in the expression from left to right until we reach an implicit data opcode and push the appropriate amount of data to the stack. So again, we're going from left to right, we see the 2, we read in these 2 bytes in different colors to make it very clear that these are 2 separate bytes. And the operation is O2 here. Again, this is like an implicit push data. It's representing a size or the number of bytes that the script expression that is probably defined on a script pub key wants you to read in from that script and put onto the execution stack. So here's the stack before the operation, blank. Here's the stack after the operation, 0, 1, 0, 0. Simple, right? Maybe. You also have these numerical data push opcodes. So numerical push data opcodes, again, I use push data here, I mean data push, are opcodes that push a number to the stack. So you have op1, op2, op3, blah, blah, all the way up to op16. And these are the numerical data push opcodes. Normally, number values are encoded as a C script num, which is it's a data format. The numerical data push opcodes allow you to avoid doing the encoding of this format and just use a single byte value to represent the number that you put. That's going to be from 1 to 16. Whatever command opcode requires numerical values, it takes the data from the stack and attempts to parse it as a C script num. So op1 allows you to make your script's pub key a simpler expression. Instead of having to think, okay, how do I encode 1 as a C script num? I can just use the byte for op1. It just makes things easier. As opposed to doing like push data or even an implicit push data like 2 and reading this in, and because then I'd have to encode something in a C script num format, especially if I have negative numbers that I'm working with. And because I don't like encoding things, encoding just makes things more complicated, I'd rather use op1, op2, blah, blah, all the way to 16 if that was my requirement for a number, if I wasn't working with big numbers. So whenever a command opcode requires numerical values, it takes the data from the stack and attempts to parse it as C script num. That's what I just said, so we're all good there. So command opcodes. Command opcodes are opcodes that take data from the stack. They perform some operation and optionally puts a result on the stack. Cool. So here's an example, op-add. One simple example of a command opcode is op-add. You have 2 arguments, x and y, that can go into op-add. So op-add would operate on 2 arguments. So this is a command that takes 2 pieces of data from the stack, converts them to C script nums, adds the values together, and puts the results onto the stack. Here's an example. So you start with an expression like this, op1, op2, op-add. Their stack starts off as empty. Then you run all the data push opcodes in the expression from left to right until we reach an operation opcode, and we place the data that we read onto the stack as we go through it. So first we read op1, we put a 1 on the stack. Then we read op2, we put the 2 on the stack. Again, these are data push opcodes. And then we hit the op-add. Now op-add is an operation. Again, I call it like a command opcode. These are terms that I made. Again, data push opcode and command opcodes are just construction I made to explain things simpler. But yeah, we reach this command opcode, and we have 1 and 2 on the stack. So now it's time to perform the operation, taking any necessary arguments as needed from right to left. So op-add takes 2 arguments, adds them, and puts the sum on the stack. So this is also important. Remember, you take from right to left. With op-add, it doesn't matter. Addition is commutative, so you could put 1 plus 2 or 2 plus 1 equals the same thing. But sometimes the order of your arguments matter depending on the command opcode that you're using, in which case you have to understand that you're going to be reading things from right to left on the stack. So here's the stack before the operation, and after this op1 and op2 are added, I would put the arguments in orange, And here's the stack after the operation. So the result is in green. 3 adds 1 and 2. Simple. All right. Now I'm going to go over something called op check sig. Op check sig is an operation that takes in a public key and a signature and checks if the private key corresponding to that public key was used to make the signature. So the only way to create transactions in the early Bitcoin software was via check sig, the closest thing to a standardness rule back then. Bitcoin used the idea of templates to see which transactions it was willing to sign. If the script didn't match a basic template, the wallet attached to your Bitcoin node would not sign the transaction. So that's pretty interesting, right? Again, we didn't have standardness, just to reiterate, we didn't have standardness back in the early days of Bitcoin. But you did have some kind of rule checking. And when Satoshi first released the software, he didn't want anyone going crazy with the scripts. So his software didn't allow you to make any crazy scripts. Instead, he kind of enforced this paradigm of only having addresses that correspond to scripts of forms like this: op check sig, pub key, and your signature. So how do scripts get run? Every node is listening for broadcasted transactions to add to their mempool. Part of the validation the node performs, I don't know why I put the apostrophe S here, but part of the validation node performs to accept the transaction to the mempool is checking the execution of a script. Now, scripts are defined when creating a transaction output, but are run when using that transaction output as an input. So you define your script when you want to receive Bitcoin, when you're making your address. The scripts that you're defining, that you made your address from, are actually executed when you're trying to spend that output with your script on it. Bitcoin node takes the script sig and executes it. So actually when you use the output with the script pub key on it, you typically when you spend it, you put this extra piece of data called the script sig. So script sig and the script pub key. You first run the script sig. The script sig could have opcodes inside of it, command and data push opcodes, and you'd execute that. You'd put some things on this shared stack, and then you'd go to the script pub key, and then you'd execute whatever is in here. And then it would take things from the stack and put things as a result, like op add. Maybe it would take two numbers that you provided in your script sig, and then it would add them together and put the result onto the stack. So the Bitcoin node takes the script sig, executes it, and executes the script pub key while giving it the same stack. We'll talk more about this in the next slide. There's actually security vulnerability that used to exist in Bitcoin when the two weren't executed separately. Before, you used to take the script sig and used to take the script pub key on the output. So script sig on the input, script pub key on the previous output, and you'd attach them together like this. Even though the script sig technically is defined an input, should come after sequentially, then a script pub key, you actually put the script sig first, and then you attach the script pub key to it. Now, I'll go over the security issue with doing that in the next slide. But I do want to end off this slide by saying for pre-SegWit transactions, if the execution of the scripts did not result in a 0 on top of the stack, then the input of the transaction being validated was allowed to be spent by the node. So when you have a script pub key, that is your locking script, and you put some expression on it, like let's say you put 3 and op equal, then you need something in your script sig that will have that script pub key put something that is non-zero on top of the stack. So op equal is opcode that checks two numbers from the top of the stack to see if they're equal, and it puts a 1 if they are and 0 otherwise. So if I had, I know it's hard to conceptualize, I don't have a visual, but if I had op equal and op3 as part of my script pub key, and then my script sig was, let's say 1, push data for 1, or let's just say op1 and op2, and I had op add, then when you put these things together, they'd actually execute and result in a 1 on top of the stack. Again, hard to visualize because I don't have a visual for it, but if you can't understand it, hopefully it helped your understanding. So here's the security issue that I was talking about in the last slide. One fatal bug to Bitcoin at the beginning of its development was the ability to put a push data opcode in the script sig and treat the entire script pub key as a data push, so it never got executed. What this means is I'm spending Bitcoin to somebody else. They gave me their address, and again, their address is some encoding of or commitment to some script that my recipient has that only they can spend. So I'm spending money to them in my output. I put their address, which again is a commitment to their script, and then let's say I wanted to spend that money back to myself. There would be a way for me to do that. I take my recipient's output and I put in a special script sig, a malicious script sig, as the unlock script for that person's locking script. And what that malicious script sig would do is it would say, hey, everything that you're about to see next is just part of my push data. So what that do is it would take the other person's script public key locking script, my script sig would say treat it all as data, it would push that data into the stack, and the Bitcoin node would validate that transaction as being valid because there was a non-zero on the stack at the end of execution. So yeah, this vulnerability allowed me to spend anyone's coins. That's what this is. So if you don't understand all the details, just know that someone else would put a locking script on a UTXO, and this vulnerability would allow me to put a special unlocking script, and it would be very easy for me to construct to spend that person's coins. So if I was the first person to discover this bug, by the way, this bug would allow me to steal everybody's coins on Bitcoin. Kind of cool, right? I mean, yeah, not cool that it existed, but cool that that it was found and solutions were made for it, I guess. So since the script pub key as data was non-zero, using this trick could bypass any script pub key and allow an attacker to spend any transaction. Okay, very bad bug. I mean, something like that today would kill Bitcoin, or some form of it. Bitcoin would always exist in some way, shape, or form, but it would cause financial havoc for sure. So the next part I want to talk about is what an interpreter is. So you have a Bitcoin node that executes Bitcoin transactions, or executes the scripts on Bitcoin transaction outputs. But how does it execute the script? And it does that using something called an interpreter. So Technopedia says an interpreter is a computer program that is used to directly execute program instructions. An interpreter takes in bytes of code and executes it. This is different from a compiler, which would take code and translate it to another language the CPU can understand, aka machine code. So Bitcoin script has its own interpreter that has been built into Bitcoin since the first release. So again, script was designed by Satoshi himself, and it was designed as part of this overall system that ended up being created. So let's talk about SegWit a little bit. SegWit was a soft fork upgrade to Bitcoin that allowed a new format for transactions. This new format would force the script sig to be empty and made the script pub key such that old upgraded nodes would never need to validate these transactions and would blindly accept them if the chain with the most hash rate had them. I meant to put unupgraded nodes. But yeah, SegWit was a change. It was a soft fork. What a soft fork means is all nodes that accept some type of upgrade that we call a soft fork now reject some types of transactions that the old nodes are broadcasting. But everything that the upgraded node sees as valid, the old nodes will see as valid as well. So as long as the majority of hash rate is on this upgrade and rejecting certain types of transactions, the old nodes will always converge onto the correct chain. That's how SegWit works. And it changed some things with the script. It, again, forced the script sig to be empty, and it actually forced the unlocked data for a locking script, which is aka the script pub key, to be moved to this new field called the witness. So it also introduced something called the witness stack. So script sig used to be another script pretty much, and when things moved to the upgraded SegWit version of transactions, you no longer had just a script as part of this unlocking data. Instead, you had something called a witness stack. And let me go over it a little bit. So the witness is a serialization of all witness fields of the transaction. Each transaction input is associated with a witness field. A witness field starts with a var int to indicate the number of stack items for the transaction input. It is followed by stack items with each starts with a var int to indicate the length. Witness data is not script. So this is very different from script sig in that your witness data is not script. This is straight from the BIPs, and they made sure to use this not all caps, right, to emphasize that this is not script. So pay to witness script hash allows maximum script size of 10,000 bytes, as the 520 byte push limit is bypassed. Okay, cool. Let's go to the next one. So I wanted to go over the witness's evolution from push-only standardness rules. So why is a script sig allowed to be a script that can be executed, and the witness not a script that is executed? Why is the witness only data that you are allowed to push onto the stack? So over the course of Bitcoin's development, standardness rules were introduced. One of the standardness rules that were introduced was for nodes to only accept transactions with push-only script sigs. This means that the script sig can only consist of data push opcodes. So even though the script sig was designed to have scripts in it, data push and command scripts, standardness rules were introduced, and part of the initial introduction of these standardness rules was to make the script sig only push data onto the stack. So they did not want command opcodes or any operations being done as part of the script sig. It only wanted to allow push data opcodes. So an evolution of this was the witness having push-only data as well, but why was this change made at all in the first place? So the motivation for push-only script sig and witness stack. I found this random article on the internet, and I thought it was a pretty informative article. I don't know how accurate it is. All the information in it is, well, it looks good. I didn't read all of it, but it looks good. And this person seems to think that, or not seems to think, they could know. I don't know. But when I was looking for the motivation, I found this. And this person seems to assert that the script sig was made to only support push data operations to reduce malleability. And I could go into that a little bit more. Sorry, 1 second. Just going to send off a message. There we go. Okay. So thanks for waiting, even though it's very low viewers. So yeah, here's what this guy says about the script sig only containing push data operations. Typically, a script sig only contains push operations. Non-push operations enable the creation of equivalent scripts in an infinite number of ways. For example, pushing 1, pushing 2, and then performing an addition operation is equivalent to pushing 3. Gavin Andreessen implemented is push only as part of standard transaction validation in December 2010. By default, this check is enabled in mainnet and disabled in testnet. So this person is saying when you allow any arbitrary script to be in your script sig and any random computation to be done in that script sig, it opens up the door for having something called transaction malleability, which is a way to broadcast a transaction to your node's mempool and have it be accepted, and then tweak or have someone else look at my transaction and find a way to tweak it just a little bit so that their tweak script is still valid and generate a completely new transaction ID that was spending my UTXO. Now, if I had a check sig in my script, typically they can't just change where my transaction is going, but some people try and be clever and make scripts that don't include a signature check, and those most of the time are very easily stolen. So script sigs help you reduce transaction malleability. And yeah, you don't want two transactions with different transaction IDs both being valid and spending the same UTXO, because that messes up certain protocols like Lightning, for example. So script interpretation is part of consensus, ... kind of. So script interpretation is part of consensus, but Softworks do introduce some complexity to the masses on what actually happens. So regular people don't really know how certain soft forks affect the Bitcoin protocol. So when SegWit was enabled, pre-SegWit nodes could accept all transactions that SegWit nodes could, but vice versa did not apply and still does not apply. So I mentioned that earlier. The SegWit specification forces all script SIGs to be empty because the data has been moved to the witness. And pre-SegWit nodes see SegWit transactions as anyone can spend because the script pub key is just version, data push, and hash of Bitcoin script. This will result in the hash of the Bitcoin script being on the top of the stack, which is non-zero and will allow the transaction to be valid by any legacy node that sees an empty script SIG on it. Okay. What was I trying to say here? I was just trying to say that the interpreter, or how scripts are run by Bitcoin nodes, are part of consensus. You can change things intelligently such that you could have a soft fork and still maintain consensus by doing whatever upgrade you want to add, and marking these upgraded transactions as anyone can spend for the old nodes, so that they don't even try and challenge these transactions. And any blocks they get with those transactions being spent in it, they'll just say, yeah, sure, it's good. It auto approves essentially. And if majority of your hash rate is using these new rules and upgrades, then you'll never get most work chain that doesn't abide by those rules. So yeah, soft forks kind of rely on majority hash rate agreeing to the change, because if it doesn't, then you'd have these old nodes potentially making a longest chain that is different from what these newer nodes think. So these newer nodes, in that case, would be the ostracized nodes and the ones who are starting to fork, not the old nodes. So here we go. I got this answer from Bitcoin Stack Exchange about this problem. So if a miner included a SegWit transaction to a block with an invalid signature, it'd be rejected by SegWit nodes, but not by non-SegWit nodes. And that is true. That's why Michael Folkson said it indeed. It would have to reach the miner, so either sent to them directly or propagated to the miner by non-SegWit nodes. SegWit nodes would reject it and not propagate it. So now, would the latter consider the transaction valid? If yes, wouldn't this result in a chain split? And here's what Michael Folkson said. I think it's kind of enlightening. He said, full nodes enforcing SegWit rules would reject a block with an invalid SegWit transaction in it, as would miners enforcing SegWit rules. What would happen in your scenario is the miner would think they're successfully mined a block, but full nodes enforcing SegWit rules would reject it, and miners enforcing SegWit rules would refuse to mine blocks on top of it. So it can cause temporary confusion amongst full nodes not enforcing SegWit rules, but the longest chain with most proof of work would end up not including that block, and that is a chain that even the full nodes not enforcing SegWit rules would end up following. So definitions aren't always clear, but there wouldn't be a lasting chain split unless a subset of miners refused to reject this block that didn't meet SegWit rules. We continued to mine in perpetuity blocks on top of it. This would be a very costly endeavor, as they would effectively be mining an altcoin and not what is considered Bitcoin. Okay, so here we're kind of talking about, in a way, chain splits, but in those cases, we always defer as the legacy rules as being valid, especially if they have majority hash rate. And if the new rules got majority hash rate, then there's no problem. Then everyone's on the same chain. Future upgrades. So there are a lot of proposals on how to change Bitcoin script, but there are many considerations to be made. Number one, there is the computational burden. So when you're thinking about new opcodes to add, you don't want to add opcodes that that would cause someone's Bitcoin node to do more computation such that they are lagging behind in the validation of Bitcoin blocks in their transactions every 10 minutes. So if a transaction took 20 minutes to validate, for example, then it would kind of break the system of Bitcoin, right? Because blocks come in every 10 minutes, and if you have one transaction that took 20 minutes to validate, then you're no longer able to meet this difficulty adjustment, and you're dramatically reducing the throughput of your Bitcoin node. So one of the things to consider when you're introducing a new opcode is the computational burden. Another thing is the space requirements for your opcode. You don't want an opcode to make it easy to balloon the space that Bitcoin transaction takes on disk, or um, or the UTXO set, which is stored in RAM. So like that's what we call in memory. And space requirements, kind of on the same topic, we have the whole thing with inscriptions, right? Inscriptions, they weren't enabled with Taproot, but they were made worse by Taproot, by some people's subjective opinions. I will withhold judgment on inscriptions. I just know that there are people out there who dislike inscriptions, and changes that would allow bigger pieces of data to be stored on chain are typically seen as undesirable by these parties. Another thing that I kind of hear from Michael Saylor on his What Bitcoin Did appearances is he seems to be cautious of opcodes that enable the potential for like additional layer 2s. In his What Bitcoin Did podcast appearance, he said that layer 2s can like find layer 2s diminish the value of miners' ASICs. So he was saying when you do soft fork upgrades to Bitcoin that allow or enable more layer 2s, you are stealing from miners and stealing their property and profit by allowing people to transact cheaply instead of being forced to pay miners higher and higher fees. And to be fair, he did say that there is a conflict of interest, maybe between those who want Bitcoin to be hard money and Bitcoin to be like self-custodied money for everybody. And maybe in that regard, I do agree with him a little bit, but I do think that that last consideration is a little bit ridiculous because, right now we have people saying, why can't you have both? We have the Lightning Network, and that needed a change back when it was first introduced. We made that change. We have the Lightning Network. It helped dramatically increase the throughput of Bitcoin transactions that could be made, and miners still aren't poor. They're still making lots of money through fees. So maybe this argument isn't as good, but it's definitely a consideration to be made. So this is summed up as people not wanting unforeseen consequences. And the big thing on people's minds right now with respect to unforeseen consequences in upgrades to Bitcoin script are covenants, which will allow a recipient to specify conditions on how they can spend Bitcoin from certain addresses. So this is helpful because the sender may only want to send Bitcoin to someone who's involved in a similar scheme to them. This might help enforce a precaution for someone stealing from the sender. So for example, Lightning, I make a funding transaction with somebody and I keep updating with commitment transactions. One of the things about like using commitment transactions is there's a delay. So if I were to generate some commitment for my counterparty, if he was going to broadcast that commitment on chain, there would be a delay. It's because I need to verify that that commitment isn't in an old state, and if it is, I need to steal all their money. So these timeouts, like things like lock time, are like it is a covenant. It has covenant mechanics to it, right? And check lock time is a covenant opcode. A lot of people don't see it that way, but you are restricting how the recipient can spend their money. Of course, the recipient isn't like being blindly forced into the scheme when they use a wallet that generates addresses. Like that was their decision. And if their address that they generated included a lock time, then that wasn't imposed by me, it was imposed by them. And maybe if I wanted to engage in some scheme with them, I would only send to the recipient if they're able to prove to me that their address was also encumbered by a similar type of lock time, So yeah, that's why people might want covenants to make new schemes. Of course, whatever covenants we introduced should not increase the computational burden, increase space requirements for a node ideally, and will not increase. Well, this one's a little bit debatable. But from Michael Saylor's perspective, he doesn't want covenants to increase the potential for additional layer twos that he would think is a way to steal money from miners and mess up the game theory of Bitcoin. Now, to this first point, I do want to say that there's Rusty Russell. He's a Bitcoin developer, and he introduced something called the Great Script Restoration Project. So if you ever see GSR on Twitter, that's what it refers to, and it is an idea to try and bound the computations of scripts on Bitcoin. Right now, a Bitcoin script can be pretty expensive to run, but that cost isn't passed on to the person who made that script, or made the address from that script. Instead, you pay by the size of your script, right? Because you're paying for the size of your transaction. But how about if I made a script that just pushes like 10 different pieces of data onto the stack, and someone else made a script that has 100 check sigs, and I mean his 100 check sigs are gonna probably be like more data because they're gonna require public keys and signatures for each, but there's no cost for him to making more expensive scripts compared to me, who's just pushing data. If I was able to have enough push datas to equal the size of all that person's 10 check sigs, then I will be charged the same amount, even though his check sigs are more computationally expensive. Now, Rusty's proposal isn't quite to charge people on the computation they use, but it is to start measuring and tracking the computation they use and enforcing some limits on what they can do, such that they can act as sanity checks if you have future opcodes that are introduced. So any future opcodes, we start measuring the computational burden of them, and the limits that we're enforcing on our Bitcoin nodes will then act as sanity checks on anything new we add. So that's what this Great Script Restoration Project is all about, GSR. Let's see, anything else here? And this is the last slide, so this is the end of my presentation. So, thanks for tuning in to what will be made into my YouTube video. And I guess I will end the stream. Yeah, thanks for tuning in, via Twitch or YouTube. Bye.